We're about to embark on a journey to one of the most extreme places in our entire solar system. A realm so scorching hot that it defies everything we think we know about temperature itself. Tonight, we're answering a question that seems deceptively simple, but leads us into the heart of stellar physics and the most mind-bending extremes of heat imaginable. How hot is the sun? It's a question that will take us from the sun's blazing surface all the way down to its nuclear furnace core, where temperatures reach levels so intense they make the hottest places on Earth look like frozen tundra. Before we dive into this cosmic inferno, feel free to comment your time and location below. There's something beautifully humbling about discussing the sun's incredible heat while we're all scattered across our small planet, each of us warmed by the same star that we're about to explore. Whether you're watching the sunset paint the sky in brilliant oranges and reds, or you're settling in for the night with only artificial light around you, remember that every bit of warmth you've ever felt ultimately traces back to the nuclear fires we're about to investigate. I would love and encourage you to watch this video until the end to discover the most shocking temperature revelations about our nearest star. But there's absolutely no problem if you drift off somewhere along the way. Let your imagination float through the layers of solar atmosphere as we uncover the secrets of stellar heat. A gentle request that if you find these explorations of cosmic phenomena fascinating, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious souls like us who have an amazing passion for understanding the universe around us. Let's begin this journey into the heart of our solar system's most powerful furnace. When you step outside on a bright summer day and feel the warmth of sunlight on your face, you're experiencing energy that began its journey in conditions so extreme they challenge the very limits of human comprehension. That gentle warmth touching your skin originated in a realm where matter exists in states so exotic that the familiar rules of physics bend and twist into something almost unrecognizable. The sun isn't just hot. It's a masterpiece of cosmic engineering, a perfectly balanced nuclear reactor that has been burning steadily for over 4.5 billion years. But here's what makes this story truly extraordinary. The heat we're about to explore doesn't follow the simple rules you might expect. As we journey from the sun's surface toward its center, we'll discover temperature gradients so steep and conditions so extreme that they rewrite everything we think we know about heat itself. Picture this for a moment. You're standing next to a campfire on a cool evening. The flames dance at around 1000 degrees Celsius, hot enough to make you step back and shield your face. Now imagine multiplying that temperature by 6. You're getting close to the heat of the sun's surface. But that's just the beginning of our story, because the sun's surface, as scorching as it sounds, is actually the coolest part of this stellar furnace. This is where our journey becomes truly mind-bending. As we travel deeper into the sun, rather than cooling down as you might expect when moving away from the surface, the temperature begins to climb in ways that defy intuition. We're about to explore temperature gradients so dramatic that they represent some of the most extreme physical conditions anywhere in our known universe. The sun's surface, called the photosphere, burns at approximately 5,800 degrees Celsius. To put this in perspective, that's hot enough to vaporize any material we know of on Earth instantly. Steel melts at around 1,500 degrees. Diamond, one of the hardest substances we know, would turn to vapor long before reaching the sun's surface temperature. Even tungsten, the metal with the highest melting point, would be nothing more than gas at these temperatures. But here's where the sun reveals its first major secret. This incredibly hot surface that we call the photosphere is actually a remarkably thin layer, only about 500 kilometers thick. Compared to the sun's total radius of nearly 700,000 kilometers, the photosphere is thinner than the skin on an apple. Yet within this thin boundary layer, we can observe some of the most fascinating temperature phenomena in our solar system. The photosphere isn't uniformly hot. It's covered in a constantly shifting pattern of bright and dark regions called granulation. These patterns look remarkably similar to what you might see on the surface of boiling water, and the comparison isn't accidental. Just like bubbles rising in a pot of boiling liquid, hot plasma from the sun's interior rises to the photosphere, cools slightly, then sinks back down in an endless convective dance. Where these hot bubbles of plasma reach the surface, we see bright granules glowing at the full temperature of the photosphere. The darker boundaries between these granules mark places where the plasma has cooled by a few hundred degrees and is sinking back into the sun's interior. These temperature variations might seem small, but they create the mottled, ever-changing appearance that gives the sun's surface its dynamic character. But the photosphere holds an even more dramatic temperature secret. Scattered across its surface are dark spots that appear almost black against the brilliant background. These are sunspots, and they represent one of the most striking examples of how magnetic fields can dramatically alter temperature on a cosmic scale. Sunspots are significantly cooler than their surroundings, with temperatures around 3,500 degrees Celsius compared to the photosphere's 5,800 degrees. This might still sound incredibly hot, and it is. A single large sunspot, isolated from the sun's bright background, would shine brighter than a full moon with a deep crimson-orange glow. But against the blazing photosphere, they appear as dark blemishes on the sun's face. What creates these cooler regions? The answer lies in the sun's powerful magnetic field. Sunspots form where magnetic field lines become concentrated and twisted, creating regions where the magnetic field strength can be thousands of times stronger than Earth's entire magnetic field. These intense magnetic fields act like invisible barriers, blocking the normal flow of hot plasma from the sun's interior to the surface. Imagine trying to heat a room with a furnace, but someone keeps closing the vents that allow hot air to flow. The room would become cooler, not because the furnace isn't working, but because the heat can't reach where it needs to go. That's essentially what happens in sunspots. The magnetic field prevents the normal convective flow of hot plasma, creating these relatively cool dark spots on the sun's surface. These sunspots can be enormous, some spanning distances greater than the diameter of Earth. They appear and disappear in cycles that last about 11 years, growing and shrinking as the sun's magnetic field undergoes its own complex rhythms. During periods of high solar activity, dozens of sunspots might pepper the sun's surface simultaneously, creating a constantly changing landscape of magnetic temperature variations. But as we prepare to journey beyond the photosphere and into the sun's atmosphere, we're about to encounter one of the most puzzling mysteries in all of solar physics. A temperature puzzle so confounding that scientists have been working to solve it for over a century and a half. As we move away from the sun's surface, logic tells us that temperatures should continue to decrease. After all, we're getting farther from the nuclear furnace at the sun's core. Yet the sun has a surprise waiting for us. Just above the photosphere lies a layer called the chromosphere, and here the temperature story takes an unexpected turn. Instead of continuing to cool as we move away from the sun's interior heat source, temperatures in the chromosphere begin to behave in ways that challenge our understanding of how heat flows through space. The chromosphere extends about 2,000 kilometers above the photosphere, a relatively thin layer that glows with a distinctive reddish color when viewed during solar eclipses. This red glow comes from superheated hydrogen gas burning at temperatures that start around 4,000 degrees at the bottom of the chromosphere, but then begin to climb dramatically as we move upward. By the time we reach the top of the chromosphere, temperatures have soared to around 20,000 degrees Celsius. Think about what this means. We've moved 2,000 kilometers farther away from the sun's core, the source of all its energy, yet the temperature has increased by a factor of 4. It's like walking away from a campfire and somehow feeling the heat getting more intense with each step. This temperature reversal in the chromosphere represents the beginning of one of the most profound mysteries in solar physics. Why does the sun get hotter as we move away from its energy source? The answer to this question will take us into the realm of magnetic fields, plasma physics, and energy transport mechanisms that operate on scales both incredibly tiny and cosmically vast. As we continue our journey outward from the sun, we're about to encounter temperature gradients so extreme they represent some of the steepest thermal boundaries anywhere in the known universe. We'll explore regions where temperatures leap by hundreds of thousands of degrees across distances smaller than the length of a major city. We'll visit plasma so hot it glows with X-rays, yet so tenuous that it's essentially a perfect vacuum by Earth standards. The sun's temperature story is just beginning to unfold, and the most shocking revelations lie ahead as we venture into the solar atmosphere's outer reaches, where the rules of heat and energy transform into something almost magical. The story of the sun's temperature becomes truly extraordinary when we venture into a region so thin it's barely there, yet so important it holds the key to understanding one of the universe's most perplexing puzzles. Between the chromosphere and what lies beyond exists a boundary layer so narrow that if the sun were the size of Earth, this region would be thinner than a major highway. This is the transition region, and here we encounter temperature changes so dramatic they redefine what we think possible in the realm of physics. Imagine standing in your kitchen, and as you take a single step forward, the temperature around you doesn't just increase by a few degrees. It doesn't even increase by hundreds of degrees. In a distance of just 100 kilometers, roughly the length of a large city, the temperature rockets from 20,000 degrees to over 500,000 degrees Celsius. To put this in perspective, if you could somehow survive in this region and take a leisurely walk from one side to the other, every single step you took would expose you to temperatures thousands of degrees hotter than the one before. It's as if the universe decided to compress an entire journey from a blast furnace to the heart of a nuclear explosion into the space of a morning jog. This transition region challenges everything we understand about how heat moves through space. On Earth, when we heat something, the temperature changes gradually. Metal slowly warms as you apply heat. Water gently comes to a boil. Even in the most extreme industrial processes, temperature changes happen over measurable distances and time periods. But here, just above the sun's surface, we're witnessing temperature gradients so steep they seem to violate the natural order of thermal physics. Scientists studying this region face a fundamental mystery. What mechanism could possibly drive such an extreme temperature jump over such a short distance? The answer isn't simply that we're getting closer to the sun's core, because we're actually moving away from it. Something else is happening here. Something that pumps enormous amounts of energy into the plasma in ways we're only beginning to understand. The transition region acts like a cosmic furnace door, separating the relatively cool chromosphere from what lies beyond. And what lies beyond represents one of the most counterintuitive discoveries in all of astronomy. As we cross through this incredibly thin boundary layer, we emerge into the sun's outermost atmosphere, the corona, where temperatures reach levels so extreme they make everything we've encountered so far seem almost chilly by comparison. The corona extends millions of kilometers into space, a ghostly realm of plasma so thin it's nearly a perfect vacuum, yet so hot it glows with temperatures that can exceed 2 million degrees Celsius. Here we find plasma heated to temperatures that are not just hotter than the sun's surface, but hundreds of times hotter. It's like discovering that the air around a campfire is somehow 300 times hotter than the flames themselves. This coronal heating mystery has puzzled scientists since the mid-1800s, when astronomers first measured these impossible temperatures during solar eclipses. How can something so far from the sun's energy source be so much hotter than regions closer to that source? It violates our everyday understanding of how heat works. When you move away from a fire, you expect to get cooler, not hundreds of times hotter. The corona presents us with plasma existing in conditions so extreme that matter behaves in ways completely foreign to our earthbound experience. Despite temperatures that would instantly vaporize any known material, the corona is so incredibly tenuous that its density is about 1 billion times less than water. If you could somehow place a container in the corona, it would contain fewer particles than the best vacuum we can create in laboratories on Earth. This creates a fascinating paradox. The corona is simultaneously scorching hot and essentially empty. It's like having an oven heated to millions of degrees, but with so few particles inside that you could theoretically put your hand in it without immediately burning, simply because there's almost nothing there to transfer that heat to you. The particles that do exist are moving at incredible speeds due to their extreme temperatures, but they're so spread out that collisions between them are remarkably rare. The coronal plasma glows with such intensity that it emits X-rays and extreme ultraviolet radiation. During a total solar eclipse, when the moon blocks the bright photosphere, the corona becomes visible as wispy white streamers extending far into space. These ethereal tendrils of superheated plasma dance and flow along magnetic field lines, creating structures that can span distances greater than the diameter of Earth. But here's what makes the coronal heating problem truly mind-bending. The energy required to heat the corona to these extreme temperatures must come from somewhere. The sun's core produces energy through nuclear fusion, but that energy travels outward and has already been significantly cooled by the time it reaches the photosphere. Something else must be adding energy to the corona, something powerful enough to heat plasma to temperatures that are hundreds of times hotter than the surface of the sun itself. Current theories focus on the sun's magnetic field as the culprit behind this cosmic heating mystery. The sun's magnetic field is incredibly complex, with field lines that twist and tangle like invisible spaghetti throughout the solar atmosphere. When these magnetic field lines become stressed and suddenly snap back into new configurations, they can release enormous amounts of energy in events called magnetic reconnection. Imagine stretching a rubber band until it snaps. When it breaks, all that stored energy is suddenly released. Now imagine this happening not with rubber bands, but with magnetic field lines carrying the energy equivalent of millions of hydrogen bombs. These magnetic explosions might be constantly occurring throughout the corona, heating the thin plasma to its extreme temperatures. Another possibility involves waves. Not sound waves like we know on Earth, but magnetic waves called alpha waves that can travel along magnetic field lines at incredible speeds. These waves might carry energy from the sun's surface up into the corona, where they dissipate their energy as heat. It's like having invisible tsunamis of magnetic energy constantly washing through the corona, each one depositing thermal energy into the already superheated plasma. Scientists have also discovered that the corona might be heated by countless tiny explosions called nanoflares. These miniature solar explosions happen hundreds of times every hour, each one releasing small amounts of energy. While individually they might seem insignificant, collectively they could provide enough energy to maintain the corona's extreme temperatures. It's like heating a house, not with one large furnace, but with millions of tiny matches being lit continuously throughout the structure. The Parker Solar Probe, humanity's most ambitious mission to touch the sun, is currently flying through the outer regions of the corona, providing our first direct measurements of this extreme environment. This remarkable spacecraft, protected by a heat shield designed to withstand temperatures hot enough to melt steel, is gathering data that might finally solve the coronal heating mystery that has puzzled scientists for over a century and a half. As the probe swoops to within just a few million kilometers of the sun's surface, traveling faster than any human-made object has ever moved, it's measuring the temperature, density, and magnetic field strength of coronal plasma directly. These measurements are providing unprecedented insights into how energy flows through the corona and what mechanisms might be responsible for heating it to such extreme temperatures. But our journey into the sun's temperature extremes is far from over. While the corona represents the hottest part of the sun's atmosphere, it's still nothing compared to the temperatures we'll encounter as we dive deeper into the sun itself. Beyond the thin photosphere, past the convective zone, where vast currents of plasma carry energy upward, lies the sun's core, where temperatures reach levels so extreme they enable the nuclear reactions that power our entire solar system. The temperature story of the sun reveals itself as a tale of extremes, mysteries, and physical processes that stretch the boundaries of what we thought possible. From the relatively cool sunspots on the surface to the million-degree corona extending into space, each layer tells us something profound about how energy, matter, and magnetic fields interact in the most extreme environments the universe has to offer. As we prepare to descend into the sun's interior, we're about to encounter temperatures that make everything we've discussed so far seem almost temperate by comparison. We're heading toward the nuclear furnace where the sun's energy is born, where hydrogen atoms collide with such violence that they fuse into helium, releasing the power that has illuminated our solar system for billions of years and will continue to do so for billions more. The journey from the corona into the sun's interior takes us across a boundary that represents one of the most dramatic transitions in temperature anywhere in the cosmos. As we leave behind the wispy tendrils of million-degree plasma dancing in the corona and begin our descent through the photosphere, we're embarking on a voyage toward temperatures so extreme they exist nowhere else in our solar system. But first, we must pass through the convection zone, a churning ocean of plasma that extends from just below the photosphere down to about 70% of the sun's radius. Here, enormous cells of superheated gas rise and fall in a cosmic ballet that has been performing continuously for over 4 billion years. These convection currents are like massive elevators of plasma, each one larger than entire continents on Earth, carrying energy upward from the sun's interior. In the convection zone, temperatures begin their relentless climb from the photosphere's relatively modest 6,000 degrees toward the unimaginable heat of the core. At the bottom of this zone, temperatures have already soared to over 2 million degrees Celsius. This is where the sun's energy, born in nuclear fire deep within the core, begins its final journey to the surface after spending tens of thousands of years working its way outward through the layers beneath. The convection zone reveals itself as a realm where plasma moves in patterns so vast they dwarf anything we can imagine on Earth. Hot plasma rises like invisible mountains of superheated gas, each convection cell spanning hundreds of thousands of kilometers. As this plasma reaches the top of the convection zone, it cools slightly and begins its downward journey, creating circulation patterns that would make Earth's weather systems look like gentle breezes by comparison. These convection currents don't just transport heat, they generate the sun's powerful magnetic field through a process that transforms the sun into a cosmic dynamo. As electrically charged plasma flows in these massive circulation patterns, it creates electrical currents that generate magnetic fields. These fields become twisted and tangled as they're carried along by the convective motion, creating the complex magnetic structures that eventually emerge at the sun's surface as sunspots, solar flares, and the intricate patterns we observe in the corona. But as remarkable as the convection zone is, it's merely the outer layer of an even more extraordinary realm. Beneath the churning convective currents lies a region where energy travels not through the movement of plasma, but through an entirely different mechanism that takes us into the realm of pure physics. This is the radiative zone, where photons of light begin an epic journey that can last tens of thousands of years. In the radiative zone, temperatures continue their steady climb as we descend deeper into the sun. Here, energy moves outward, not through convection, but through radiation. Photons created in the nuclear reactions at the sun's core begin their tortuous journey toward the surface. But this isn't a straight path by any means. Each photon travels only a tiny distance before being absorbed by an atom, which then re-emits it in a random direction. This creates one of the most mind-bending aspects of solar physics. A photon created today in the sun's core won't reach the surface for somewhere between 10,000 and 100,000 years. That's because each photon must undergo countless absorptions and re-emissions, following what scientists call a random walk through the dense plasma of the radiative zone. It's like trying to walk across a crowded room while blindfolded, bumping into people constantly and being redirected in random directions with each collision. The radiative zone extends from about 25% of the sun's radius out to the bottom of the convection zone. Throughout this vast region, temperatures steadily increase as we move inward, climbing from 2 million degrees at the top to over 7 million degrees at the bottom. The plasma here is so dense and hot that it exists in conditions completely foreign to anything we experience on Earth. At these temperatures, matter behaves in ways that challenge our everyday understanding. Atoms are completely stripped of their electrons, existing as naked nuclei surrounded by a sea of free electrons. This creates a state of matter called plasma, but plasma so hot and dense that it's unlike anything we can create in terrestrial laboratories. The pressure at these depths is millions of times greater than atmospheric pressure on Earth, crushing matter into densities that approach the limits of what ordinary matter can achieve. Yet even these extreme conditions pale in comparison to what awaits us at the very heart of our nearest star. As we approach the boundary between the radiative zone and the core, we're entering territory where the fundamental forces of nature engage in a cosmic wrestling match that has been powering our solar system since before Earth even existed. The Sun's core occupies only about 3% of the Sun's total volume, yet it contains more than 30% of the Sun's entire mass. This creates a gravitational furnace so intense that it transforms the very nature of matter itself. Here, in a sphere roughly the size of Jupiter, but containing more mass than 200 Earths, we encounter temperatures that represent the most extreme thermal conditions in our solar system. At 15 million degrees Celsius, the core's temperature is so intense that it enables nuclear fusion on a scale that defies comprehension. Every second, the Sun's core converts 600 million tons of hydrogen into helium through a process that releases energy equivalent to billions of hydrogen bombs detonating simultaneously. This isn't a violent explosion, but rather a controlled nuclear furnace that has been burning steadily for over 4.5 billion years. The nuclear reactions occurring in the core follow a precise sequence known as the proton-proton chain reaction. At temperatures of 15 million degrees, hydrogen nuclei move so fast that they can overcome the electrical force that normally keeps them apart. When two protons collide with sufficient energy, they can fuse together, beginning a chain of reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus. But here's what makes this process truly remarkable. The core temperature isn't just hot enough to enable fusion, it's precisely the right temperature to sustain it in perfect balance. If the core were slightly cooler, fusion reactions would slow down, the Sun would begin to contract under its own gravity, and the increased pressure would heat the core until fusion resumed. If the core were hotter, fusion would accelerate, the Sun would expand, pressure would decrease, and the core would cool until equilibrium was restored. This creates a cosmic thermostat that has kept our Sun burning at a steady rate for billions of years. The Sun is essentially a self-regulating nuclear reactor, maintaining the perfect balance between the inward pull of gravity and the outward pressure of nuclear fusion. This delicate equilibrium is what has allowed life to flourish on Earth, providing a steady source of energy that has remained remarkably constant throughout the history of our planet. The energy released by fusion in the core is so immense that each second the Sun converts about 4 million tons of matter directly into energy, according to Einstein's famous equation. This energy begins its journey as high-energy gamma rays. But as these photons work their way outward through the radiative zone, they undergo countless interactions that gradually transform them into the visible light that eventually reaches Earth. The core's density is equally astounding, reaching 150 times the density of water at its center. At this density, a sugar cube-sized piece of core material would weigh as much as a small car. The pressure at the core's center is over 200 billion times Earth's atmospheric pressure, creating conditions so extreme that matter is compressed to its absolute limits. Yet despite these incredible extremes, the core generates energy at a surprisingly gentle rate when considered per unit volume. The power density of the Sun's core is actually lower than that of human metabolism. A person generates more energy per kilogram than the same mass of solar core material. The Sun's enormous energy output comes not from the intensity of fusion reactions, but from the sheer volume of material undergoing fusion simultaneously. This gentle energy production is what allows the Sun to burn steadily for billions of years. Unlike a bomb, which releases all its energy in an instant, or a fire, which consumes fuel rapidly, the Sun's nuclear reactions proceed at exactly the rate needed to balance gravitational collapse. It's a cosmic dance between the fundamental forces that has been choreographed by the laws of physics to create the stable star that makes life on Earth possible. The core's magnetic field adds another layer of complexity to this already extraordinary environment. The intense heat and pressure create conditions where magnetic fields can become trapped and amplified, contributing to the complex magnetic structures that eventually emerge at the Sun's surface. These fields play a crucial role in transporting energy and regulating the fusion process itself. As we contemplate these core temperatures of 15 million degrees, we're witnessing the fundamental process that powers not just our Sun, but virtually every star in the universe. This nuclear furnace represents the ultimate source of almost all energy on Earth. The coal we burn was formed by ancient plants that captured sunlight. The wind that turns our turbines is driven by solar heating of Earth's atmosphere. Even the food we eat contains energy that was originally created in stellar cores like the one we're exploring. The temperature journey from the Sun's core to its corona reveals a story of energy transformation that spans scales from the subatomic to the cosmic. Nuclear reactions create energy in the core. That energy slowly works its way outward over thousands of years, emerges as visible light from the photosphere, and somehow gets redirected and amplified to create the million-degree corona that extends far into space. Each temperature regime tells us something profound about how the universe works at its most fundamental level. From the quantum mechanics governing fusion reactions in the 15 million degree core to the plasma physics of the million-degree corona, the Sun serves as a natural laboratory for studying physical processes under conditions we could never recreate on Earth. As we prepare to explore how these extreme temperatures compare to other objects in our solar system and beyond, we're beginning to appreciate that the Sun isn't just hot by earthly standards. It represents one of the most successful nuclear reactors in our cosmic neighborhood, a stellar furnace that has been converting matter into energy with remarkable efficiency for longer than life has existed on Earth, and will continue to do so for billions of years to come. The Sun's extraordinary temperature story becomes even more fascinating when we begin comparing these stellar extremes to everything else in our cosmic neighborhood. To truly appreciate the mind-bending heat we've been exploring, we need to step back and consider just how unique these temperatures are in the context of our solar system and beyond. Let's start with something familiar. The hottest temperature ever recorded on Earth reached just 57 degrees Celsius in Death Valley. Even our most extreme industrial processes, like steel production, operate at temperatures around 1600 degrees Celsius. The core of our planet, subjected to immense pressure from all the rock above it, reaches temperatures of perhaps 6000 degrees Celsius. These seem like impressive numbers until we remember that the Sun's surface, its coolest visible layer, burns at nearly 6000 degrees, while its core blazes at 15 million degrees. To put this in perspective, imagine if you could somehow transport a pinhead-sized piece of the Sun's core to Earth. That tiny fragment would contain enough thermal energy to kill a person from over 150 kilometers away. The heat would be so intense that it would be lethal at distances greater than the length of some countries. This isn't science fiction. This is the reality of temperatures that exist just 93 million miles away from us, close enough that their energy reaches us in just 8 minutes and 20 seconds. But perhaps the most startling comparison comes when we look at other objects in our solar system. Venus, often called Earth's evil twin, experiences a runaway greenhouse effect that makes it the hottest planet in our solar system. Its surface temperature reaches a scorching 470 degrees Celsius, hot enough to melt lead and zinc. Yet this infernal world, hot enough to destroy most metals, is still cooler than the Sun's surface by a factor of 12. Jupiter, that massive gas giant with more mass than all other planets combined, generates its own heat through gravitational compression. Deep in Jupiter's core, pressures and temperatures rise to levels that create some of the most extreme conditions found on any planet. Scientists estimate that Jupiter's core reaches temperatures around 20,000 degrees Celsius, hot enough to vaporize any known material. Yet even this planetary furnace is still cooler than the Sun's chromosphere and utterly insignificant compared to the solar core. The comparison becomes truly staggering when we consider the vast emptiness of space itself. The cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space, maintains a temperature of just 2.7 degrees above absolute zero. This means that space itself is nearly 300 degrees below freezing. The contrast between the Sun's 15 million degree core and the 2.7 degree background of space represents one of the most extreme temperature gradients anywhere in the known universe. Even more remarkable is how the Sun maintains these incredible temperatures through a delicate balance that has persisted for billions of years. Most hot objects cool down over time as they radiate their heat away into space. A piece of hot metal eventually reaches room temperature. A cup of coffee grows cold if left sitting too long. Even planets slowly lose their internal heat over geological time scales. But the Sun is different. Rather than cooling down, it generates new heat continuously through nuclear fusion, replacing the energy it radiates into space with fresh thermal energy created from the conversion of matter. This process is so efficient that the Sun has been maintaining essentially constant temperatures for longer than life has existed on Earth, and it will continue to do so for approximately another 5 billion years. The nuclear reactions powering these extreme temperatures follow principles that seem almost magical in their precision. Every second, deep in the Sun's core, approximately 600 million tons of hydrogen undergo fusion to create helium. The mass of the resulting helium is slightly less than the original hydrogen, and that missing mass becomes pure energy, according to Einstein's famous equation. This mass-to-energy conversion is so efficient that losing just 4 million tons of matter per second provides enough energy to power the entire sun. To understand how efficient this process is, consider that the sun converts matter to energy at a rate of about 0.7%. This means that when hydrogen fuses into helium, less than 1% of the original mass becomes energy, while over 99% remains as matter. Yet this tiny conversion is enough to generate temperatures of 15 million degrees and maintain them for billions of years. The precision required for this process to work is almost incomprehensible. The nuclear reactions in the sun's core depend on a process called quantum tunneling, where hydrogen nuclei overcome their electrical repulsion through quantum mechanical effects. At 15 million degrees, hydrogen nuclei move fast enough that they occasionally tunnel through the energy barrier that would normally keep them apart, allowing fusion to occur. If the temperature were just a few percent lower, fusion would become so rare that the sun would begin to collapse under its own gravity. If the temperature were just a few percent higher, fusion would proceed so rapidly that the sun would expand and potentially become unstable. The 15 million degree temperature of the core represents a perfect balance point where fusion occurs at exactly the right rate to maintain stellar equilibrium. This temperature also determines the types of fusion reactions that can occur. In the sun's core, the primary process is hydrogen fusion, which requires temperatures above 10 million degrees. Stars with different masses and different core temperatures undergo different types of fusion. More massive stars with hotter cores can fuse heavier elements like carbon, oxygen, and even iron. The hottest stellar cores in the universe can reach temperatures over 3 billion degrees, hot enough to create the heaviest elements through explosive nucleosynthesis. The sun's temperature profile also reveals something profound about how energy moves through different environments. In the core, energy is created through fusion and begins its journey outward as high-energy gamma rays. These photons carry tremendous amounts of energy, but they can only travel tiny distances before being absorbed and re-emitted by the surrounding plasma. As these photons work their way through the radiative zone, they undergo millions of absorption and re-emission events. Each time a photon is absorbed and re-emitted, it loses a small amount of energy and shifts toward longer wavelengths. By the time the energy reaches the convection zone, the original gamma rays have been transformed into lower energy photons that can be transported more easily by the movement of plasma. This energy transport process creates the temperature gradient we observe throughout the sun's interior. The core must be hottest, because that's where energy is being created. Each successive layer outward is slightly cooler, because energy is flowing from hot regions to cooler ones. The temperature profile we measure, from 15 million degrees at the center to 6,000 degrees at the surface, represents the steady-state solution to this energy transport equation. The magnetic fields generated by the sun's rotation and convection add another layer of complexity to this temperature story. These magnetic fields can trap and concentrate energy, creating regions of enhanced heating. They can also redirect energy flow, causing some areas to become hotter or cooler than they would be based on thermal transport alone. The coronal heating mystery we explored earlier represents perhaps the most dramatic example of magnetic fields affecting temperature. The magnetic energy stored in the sun's field lines can be released suddenly through reconnection events, heating the corona to temperatures that far exceed the photosphere below. This process essentially uses magnetic energy as a secondary heating mechanism, capable of creating temperature inversions that defy our everyday understanding of heat flow. Current space missions are providing unprecedented insights into these temperature extremes and the processes that create them. The Parker Solar Probe, flying closer to the Sun than any previous spacecraft, is measuring temperatures and magnetic fields directly in the corona. The Solar Orbiter mission is capturing images of the Sun's surface at resolutions that reveal the fine details of how magnetic fields and temperature variations interact. These missions are discovering that the Sun's temperature story is even more complex than we previously understood. They're finding evidence of heating mechanisms that operate on multiple scales simultaneously, from tiny nanoflares that occur constantly throughout the corona to massive coronal mass ejections that can heat plasma to tens of millions of degrees and hurl it across the solar system at speeds exceeding 1 million miles per hour. The temperature measurements from these spacecraft are also revealing how solar activity affects the thermal structure of the Sun's atmosphere. During periods of high solar activity, when sunspots and solar flares are common, the corona becomes hotter and more dynamic. During quiet periods when the Sun's magnetic field is more stable, coronal temperatures are lower and more uniform. These variations in solar temperature have direct consequences for Earth and the other planets. The solar wind, a stream of charged particles flowing from the corona, carries thermal energy throughout the solar system. When the corona is hotter, the solar wind is faster and more energetic. When coronal temperatures are lower, the solar wind becomes gentler and less intense. The Sun's temperature story thus extends far beyond the Sun itself, influencing the thermal environment of every planet, moon, asteroid, and comet in our solar system. The energy that began its journey in the 15 million degree core eventually determines the climate of Earth, the atmospheric dynamics of Venus, the seasonal changes on Mars, and the complex chemistry occurring in the atmospheres of the giant planets. As we continue to study these extreme temperatures and the processes that create them, we're gaining insights that extend far beyond our own star. The nuclear physics occurring in the Sun's core is similar to processes in stars throughout the galaxy. The magnetic heating mechanisms operating in the solar corona likely occur in stellar atmospheres around other stars as well. Understanding the Sun's temperature extremes thus provides a window into the thermal processes that power the universe itself. Every star we see in the night sky is powered by nuclear fusion occurring at temperatures similar to our Sun's core. Every stellar atmosphere likely experiences some form of magnetic heating, similar to what creates our Sun's hot corona. The temperature story of the Sun reveals itself as more than just a tale of extreme heat. It's a story about the fundamental processes that make stars possible, that create the energy necessary for planets to form and life to evolve, and that will ultimately determine the fate of our solar system billions of years from now. These temperatures, so extreme they challenge our imagination, are also precisely tuned to create the stable, long-lived star that has made our existence possible. As we stand at the threshold of understanding these cosmic temperature extremes, we encounter one final revelation that transforms our entire perspective on stellar heat. The sun's temperature story isn't just about numbers on a thermometer or exotic states of plasma. It's about the fundamental architecture of how energy flows through the universe, creating the conditions necessary for complexity, chemistry, and ultimately life itself to emerge. Consider for a moment the extraordinary chain of events that these temperatures make possible. Deep in the core, at 15 million degrees, hydrogen nuclei overcome their natural repulsion and fuse into helium, releasing energy in the form of gamma rays. These high-energy photons begin an epic journey that will take tens of thousands of years to complete, slowly working their way through the dense plasma of the radiative zone. But here's what makes this process truly remarkable. As these gamma rays travel outward, they don't just transport energy, they transform it. Each time a photon is absorbed and re-emitted by an atom in the sun's interior, it loses a tiny amount of energy and shifts to a slightly longer wavelength. By the time this energy reaches the photosphere, the original gamma rays have been transformed into the visible light that illuminates our world. This transformation process is like a cosmic alchemy, taking the raw nuclear fire of the core and converting it into the gentle warmth that makes Earth habitable. The sun acts as a vast energy processing facility, taking the violent energy of nuclear fusion and moderating it into something that can nurture life rather than destroy it. The temperature gradient from core to corona also reveals something profound about information and causality in stellar systems. Changes in the core's fusion rate don't immediately affect the sun's brightness. Instead, they must propagate outward through the radiative zone at the speed of light, but through a medium so dense that photons can only travel microscopic distances before being scattered. This creates a natural delay system that stabilizes the sun's energy output over timescales relevant to planetary evolution. When we examine the magnetic heating of the corona, we discover another layer of this cosmic temperature story. The million-degree plasma streaming away from the sun in the solar wind carries with it a thermal signature that extends throughout our entire solar system. This superheated gas doesn't just dissipate into space. It creates the heliosphere, a vast bubble of solar influence that extends far beyond the orbit of Pluto. Within this bubble, the thermal energy that originated in nuclear fusion reactions continues to shape the environment around every planet. On Earth, the solar wind interacts with our magnetic field to create the auroras, those dancing curtains of light that appear near the poles. These auroras are essentially visible manifestations of the sun's coronal temperatures, as particles heated to millions of degrees in the corona collide with our atmosphere and create the spectacular light displays. The temperature extremes we've explored also play a crucial role in the chemical evolution of our solar system. The nuclear fusion occurring at 15 million degrees in the sun's core doesn't just convert hydrogen to helium. Over the sun's lifetime, it will gradually change the composition of the core, slowly increasing the proportion of helium relative to hydrogen. This compositional change will eventually alter the core's temperature and pressure, causing the fusion rate to increase slowly over billions of years. As the sun ages, its core will become slightly hotter and denser, leading to increased energy output. This gradual warming represents a slow but steady increase in the thermal energy reaching Earth, with implications for our planet's climate over geological timescales. But the sun's temperature story extends beyond its current stable burning phase. In approximately 5 billion years, when the hydrogen in the core becomes depleted, the sun will undergo dramatic temperature changes that will transform it into an entirely different type of star. As hydrogen fusion in the core slows down, the core will begin to contract under its own gravity, causing temperatures to rise even higher than they are today. This increased core temperature will eventually become hot enough to ignite helium fusion, a process that requires temperatures exceeding 100 million degrees. When helium burning begins, it will release even more energy than hydrogen fusion, causing the Sun to expand dramatically and become what astronomers call a red giant star. During this red giant phase, the Sun's outer layers will expand to enormous size while cooling to temperatures around 3,000 degrees. The contrast between the incredibly hot helium-burning core and the relatively cool extended atmosphere will create temperature gradients even more extreme than what we observe today. These future temperature changes illustrate how stellar evolution is fundamentally driven by the balance between gravitational compression and thermal pressure. As the Sun exhausts different types of nuclear fuel, its internal temperature structure will reorganize repeatedly, each time creating new equilibrium conditions that determine the star's size, brightness, and surface temperature. The study of solar temperatures also provides crucial insights into how other stars evolve and die. Stars more massive than the Sun can achieve even higher core temperatures, hot enough to fuse increasingly heavy elements through successive burning phases. The most massive stars can reach core temperatures exceeding 3 billion degrees, hot enough to synthesize elements as heavy as iron through nuclear fusion. When these massive stars exhaust their nuclear fuel, they undergo catastrophic collapse, followed by explosive rebounding in events called supernovae. During these explosions, temperatures can briefly reach over 100 billion degrees, hot enough to create elements heavier than iron through rapid neutron capture processes. The gold in your jewelry, the uranium in nuclear reactors, and many other heavy elements were forged in these stellar furnaces at temperatures that dwarf even the Sun's core. The temperature measurements we've explored also connect our Sun to the broader cosmos in unexpected ways. The cosmic microwave background radiation that fills all of space represents the cooled remnant of the Big Bang, when the entire universe was hotter than the center of the Sun. As the universe expanded and cooled over billions of years, this primordial heat faded to just 2.7 degrees above absolute zero. Yet within this cold cosmic backdrop, stars like our Sun create islands of intense heat through gravitational collapse and nuclear fusion. The Sun's 15 million degree core represents a local reversal of the universe's overall cooling trend, a pocket of extreme temperature maintained by the fundamental forces of physics working in perfect balance. Modern space-based observatories are revealing that similar temperature extremes exist throughout the galaxy. The Hubble Space Telescope and other instruments can measure the surface temperatures of distant stars by analyzing their light spectra. They've discovered stars with surface temperatures ranging from less than 3,000 degrees for cool red dwarfs to over 50,000 degrees for the hottest blue giants. These observations reveal that our Sun, with its surface temperature of nearly 6,000 degrees, represents a middle ground in the stellar temperature spectrum. It's hot enough to sustain stable nuclear fusion for billions of years, yet cool enough to allow complex chemistry to occur on nearby planets. This temperature sweet spot may be crucial for the development of planetary systems capable of supporting life. The precision instruments aboard spacecraft, like the Solar Dynamics Observatory, are also revealing that the Sun's temperature varies in subtle but important ways over timescales ranging from minutes to decades. Solar flares can briefly heat small regions of the corona to temperatures exceeding 10 million degrees, while the 11-year solar cycle causes more gradual changes in average coronal temperature. These temperature variations have measurable effects on Earth's upper atmosphere, space weather, and even our planet's climate. During periods of high solar activity, increased coronal heating leads to stronger solar wind and more intense magnetic storms. During quiet periods, reduced coronal temperatures result in gentler space weather conditions. The study of solar temperatures has also led to breakthroughs in plasma physics that have applications far beyond astronomy. The extreme conditions in the Sun's atmosphere have inspired the development of controlled fusion reactors on Earth, where scientists are attempting to recreate stellar core conditions in magnetic containment systems. These fusion experiments require heating hydrogen plasma to temperatures approaching 100 million degrees, even hotter than the Sun's core. Because terrestrial reactors cannot achieve the enormous gravitational pressures that make fusion possible at lower temperatures in stellar cores. The challenge of creating and controlling such extreme temperatures represents one of the frontiers of modern physics and engineering. As we reflect on this journey through the Sun's temperature extremes, we discover that we've been exploring more than just stellar physics. We've been investigating the fundamental processes that make complexity possible in the universe. The nuclear fusion occurring at 15 million degrees creates the elements necessary for rocky planets. The magnetic heating of the corona drives the solar wind that shapes planetary atmospheres. The precise temperature balance maintains stable energy output over the billions of years necessary for biological evolution. Every atom of carbon in your body was forged in the core of a star at temperatures similar to our Sun's nuclear furnace. Every breath of oxygen you take was created through stellar nucleosynthesis at millions of degrees. The iron in your blood was synthesized in the final moments of a massive star's life, in a core heated to billions of degrees before exploding as a supernova. The Sun's temperature story thus becomes our story, connecting us to the cosmic processes that created the elements of life itself. We are not separate observers studying a distant star. We are participants in an ongoing cosmic evolution, temporary arrangements of stellar matter that have achieved the remarkable feat of consciousness, enabling the universe to contemplate its own thermal extremes. Tonight, as you drift towards sleep, remember that every bit of warmth you feel traces back to these nuclear fires burning at 15 million degrees. The gentle heat of your blanket, the thermal energy maintaining your body temperature, the infrared radiation warming your room, all of it ultimately derives from the fusion reactions occurring in our nearest star. The Sun's temperature extremes remind us that we live in a universe of incredible diversity and beauty, where matter can exist in states ranging from the near absolute zero of deep space to the 100 billion degree infernos of stellar explosions. Yet within this vast range of thermal conditions, our Sun occupies a special place, maintaining exactly the temperatures necessary to power a stable, life-supporting star. As you close your eyes and let the day's thoughts settle, know that you rest under the influence of one of the universe's most remarkable thermal engines, a nuclear furnace whose 15 million degree core has been burning steadily since before the Earth formed and will continue illuminating our cosmic neighborhood for billions of years to come. The heat that began its journey in conditions so extreme they challenge human comprehension, now surrounds you as the gentle warmth that makes all life possible, connecting you to the deepest mysteries of stellar physics and the ongoing story of cosmic evolution itself. But as we prepare to conclude our exploration of the sun's thermal mysteries, we encounter perhaps the most humbling realization of all. These temperature extremes that we've been investigating aren't just abstract numbers or distant phenomena. They represent the fundamental rhythm of existence itself, the cosmic heartbeat that has been sustaining life in our solar system for over 4 billion years. The journey we've taken together, from the relatively cool sunspots on the photosphere to the 15 million degree nuclear furnace at the core, reveals something profound about the nature of energy and matter in our universe. Each temperature zone tells its own story about how the fundamental forces of physics interact to create the conditions necessary for stars, planets, and ultimately life to exist. Consider how remarkable it is that we can even measure these temperatures. The techniques scientists use to determine that the sun's core burns at 15 million degrees represent some of the most ingenious applications of physics and mathematics ever devised. We cannot send thermometers to the sun's center, yet through careful analysis of the light reaching Earth, measurement of nuclear reaction rates, and sophisticated computer modeling, we can peer into the heart of our nearest star with extraordinary precision. The neutrino detectors buried deep underground on Earth capture ghostly particles created in the sun's core, providing direct evidence of the nuclear reactions occurring at those incredible temperatures. These nearly massless particles travel at nearly the speed of light from the core to Earth's surface, carrying with them information about fusion processes happening at 15 million degrees. When we detect these neutrinos, we're literally catching messengers from the sun's nuclear furnace. The spectroscopic analysis of sunlight reveals the temperature structure of the solar atmosphere with remarkable detail. Each wavelength of light carries information about the temperature of the region where it was emitted. By carefully analyzing these spectral signatures, astronomers can map the temperature variations throughout the chromosphere, transition region, and corona with precision that would have seemed impossible just decades ago. Satellite missions have revolutionized our understanding of solar temperatures by providing observations from outside Earth's atmosphere. The Solar Dynamics Observatory captures images of the sun in multiple wavelengths simultaneously, each one revealing different temperature regimes. Ultraviolet images show the hot chromosphere and transition region, while extreme ultraviolet and X-ray observations reveal the million-degree corona in exquisite detail. These space-based observations have revealed that the sun's temperature structure is far more dynamic and complex than early astronomers imagined. Rather than smooth, uniform layers, the solar atmosphere exhibits intricate structure on scales ranging from hundreds of kilometers to hundreds of thousands of kilometers. Coronal loops, heated to several million degrees, arch high above the photosphere following magnetic field lines. Solar prominences, cooler clouds of plasma suspended in the hot corona, create dramatic temperature contrasts visible during eclipses. The magnetic field plays such a crucial role in determining these temperature patterns that solar physicists now think of the sun as fundamentally a magnetic star rather than simply a gas ball. The complex topology of magnetic field lines threading through the solar atmosphere creates a three-dimensional network of heating and cooling regions that determines where plasma reaches millions of degrees and where it remains relatively cool. Recent computational models of solar magnetism have revealed that the Sun's magnetic field is continuously regenerating itself through a process called the solar dynamo. The rotation of the Sun, combined with convective motion in the outer layers, twists and amplifies magnetic field lines in an 11-year cycle. This cycle directly affects the temperature structure of the corona, with periods of high magnetic activity corresponding to increased coronal heating and more extreme temperature gradients. The implications of these temperature extremes extend far beyond the Sun itself. The solar wind, streaming away from the million-degree corona, creates a vast region of space dominated by solar influence called the heliosphere. This bubble of solar plasma extends well beyond the orbit of Pluto, creating the local environment within which all planetary processes occur. The temperature of the solar wind as it flows past Earth varies depending on its source region in the corona. Fast solar wind streams, originating from coronal holes where temperatures are slightly lower, travel at speeds exceeding 700 kilometers per second. Slow solar wind, emerging from regions of more intense coronal heating, moves at around 400 kilometers per second, but carries more thermal energy per particle. These variations in solar wind temperature and speed directly influence Earth's magnetosphere and upper atmosphere. During periods when hot, dense solar wind encounters Earth's magnetic field, the resulting magnetic storms can heat our planet's upper atmosphere enough to cause satellites to experience increased atmospheric drag. The aurora displays that result from these interactions are essentially visible manifestations of solar temperatures, as particles heated to millions of degrees in the corona transfer their energy to Earth's atmosphere. The long-term evolution of solar temperatures also has profound implications for the future habitability of our planet. As the Sun gradually ages and the composition of its core changes, the core temperature will slowly increase. This will lead to a gradual brightening of the Sun over timescales of hundreds of millions to billions of years. Climate models suggest that this slow solar brightening, driven by increasing core temperatures, will eventually make Earth too hot to support liquid water on its surface. In about 1 billion years, long before the Sun exhausts its hydrogen fuel, our planet may become as hot as Venus is today. This represents the ultimate temperature-driven limit to the longevity of Earth's biosphere. Yet this same process of stellar evolution has made our current existence possible. Early in the Sun's life, when it was about 30% dimmer than today, Earth would have been much colder. The gradual warming caused by slowly increasing core temperatures helped maintain habitable conditions on our planet, even as the composition of Earth's atmosphere changed over geological time. The study of solar temperatures also provides crucial insights into the potential habitability of planets around other stars. Astronomers have now discovered thousands of exoplanets, many of them orbiting stars with different masses and temperatures than our Sun. By understanding how stellar mass and core temperature affect energy output, scientists can estimate which of these distant worlds might have surface temperatures suitable for liquid water. Red dwarf stars, which are cooler and less massive than the Sun, burn their hydrogen fuel at much lower core temperatures and can maintain stable fusion for trillions of years. However, their lower surface temperatures mean that planets must orbit much closer to receive enough heat for habitability. This proximity subjects these worlds to intense stellar radiation and potential tidal heating that could affect their atmospheric evolution. More massive stars than the Sun achieve higher core temperatures and burn much brighter, but they also exhaust their fuel much faster. These hot blue stars may only burn for millions rather than billions of years, potentially not providing enough time for complex life to evolve on nearby planets. The Sun's intermediate mass and moderate core temperature may represent an optimal balance for supporting long-term planetary habitability. The precision of temperature measurements in modern solar physics has also revealed subtle but important effects that influence Earth's climate over shorter timescales. The total solar irradiance, the amount of energy reaching Earth from the Sun, varies by about 0.1% over the 11-year solar cycle as coronal temperatures and magnetic activity change. While this variation might seem small, it's sufficient to influence atmospheric circulation patterns and regional climate variations on Earth. Some studies suggest correlations between periods of unusually low solar activity, when coronal temperatures are reduced, and cooler periods in Earth's climate history, such as the Little Ice Age. The temperature extremes we've explored also connect to some of the most fundamental questions in physics about the nature of matter and energy. The conditions in the Sun's core, with temperatures of 15 million degrees and pressures billions of times greater than Earth's atmosphere, allow us to test theories about how matter behaves under extreme conditions that cannot be replicated in terrestrial laboratories. The nuclear physics occurring at these temperatures follows quantum mechanical principles that seem almost magical in their precision. The probability that two hydrogen nuclei will overcome their electrical repulsion and fuse together depends exponentially on temperature. Small changes in core temperature lead to dramatic changes in fusion rate, creating the delicate balance that has allowed the Sun to burn steadily for billions of years. Advanced computer simulations now allow scientists to model these nuclear processes with remarkable accuracy, predicting fusion rates and energy production throughout the Sun's interior. These models reveal that the Sun's core is not uniform, but exhibits complex three-dimensional structure with regions of slightly different temperature and composition that evolve over time. The magnetic fields generated by these temperature and density variations in the core may contribute to the complex magnetic structures we observe at the Sun's surface. Some theories suggest that magnetic fields created deep in the solar interior can influence the dynamo process that generates the Sun's overall magnetic field, creating connections between nuclear fusion temperatures and coronal heating that span the entire star. As space technology continues to advance, future missions will provide even more detailed measurements of solar temperatures. The European Solar Orbiter mission is designed to observe the Sun from high solar latitudes, providing views of the polar regions that are difficult to study from Earth's orbital plane. These observations may reveal temperature variations in polar coronal holes that could help solve remaining mysteries about coronal heating. Proposed future missions might even attempt to send probes deeper into the solar atmosphere than ever before, potentially measuring coronal temperatures directly with in-situ instruments. Such measurements would provide unprecedented insights into the heating mechanisms that create million-degree plasma in the Sun's outer atmosphere. Ground-based solar telescopes are also becoming increasingly sophisticated, with adaptive optics systems that can correct for atmospheric turbulence and reveal temperature variations on the Sun's surface, with spatial resolutions of just a few hundred kilometers. These observations are revealing the fine-scale structure of convection patterns and magnetic fields that ultimately drive all the temperature extremes we observe throughout the solar atmosphere. The Daniel K. Inouye Solar Telescope in Hawaii, currently the world's largest solar telescope, can resolve features on the Sun's surface smaller than Earth's smallest countries. Its observations are revealing how magnetic fields and convective motions interact on the smallest observable scales, providing crucial data for understanding how energy flows from the Sun's interior to its corona. These technological advances are transforming our understanding of solar temperatures from a collection of average values to a detailed, dynamic picture of how thermal energy moves through a complex, three-dimensional magnetic environment. We're beginning to see the Sun not as a simple sphere with well-defined layers, but as an intricate system where temperature, magnetic field, and plasma motion are intimately connected across all spatial and temporal scales. The temperature story of the Sun ultimately reveals itself as a story about the fundamental processes that make complexity possible in the universe. Nuclear fusion at 15 million degrees creates the chemical elements necessary for rocky planets and biological molecules. Magnetic heating of the corona to millions of degrees drives the solar wind that shapes planetary atmospheres and magnetospheres. The precise balance of temperatures throughout the solar interior maintains stable energy output over the billions of years necessary for biological evolution. Every aspect of the Sun's thermal structure contributes to creating and maintaining the conditions that make life possible on Earth. From the nuclear furnace that converts hydrogen to helium, to the convective motions that transport energy outward, to the magnetic processes that heat the corona, each temperature regime plays a crucial role in sustaining our solar system's habitability. As we conclude this journey through the Sun's temperature extremes, we're left with a profound appreciation for the delicate balance of physical processes that creates and maintains our nearest star. The 15 million degrees at the core, the thousands of degrees in sunspots, the millions of degrees in the corona, each represents a precisely tuned aspect of a cosmic system that has been providing stable, life-sustaining energy for over 4 billion years. These temperatures, so extreme they challenge our imagination, are also exactly what they need to be to create the star that makes our existence possible. In understanding how hot the Sun truly is, we discover not just numbers on a cosmic thermometer, but the fundamental thermal architecture that connects nuclear physics to planetary habitability, quantum mechanics to stellar evolution, and ultimately, the deepest mysteries of stellar fire to the ongoing story of life in our universe. The Sun's temperature extremes remind us that we live in a cosmos where matter can exist in states ranging from the near absolute zero of deep space to the 100 billion degree infernos of stellar explosions. Yet within this vast range of thermal conditions, our Sun occupies a special place, maintaining exactly the temperatures necessary to power a stable, long-lived, life-supporting star that continues to illuminate our cosmic neighborhood with the gentle warmth that makes all earthly existence possible. Tonight, as you settle deeper into contemplation of these cosmic truths, we encounter one final temperature mystery that reveals just how interconnected our Sun's thermal story truly is. Deep beneath the surface, in regions we've barely begun to explore, lies evidence of temperature variations that challenge everything we thought we knew about stellar structure. The radiative zone, that vast realm where energy creeps outward through countless photon interactions, isn't the uniform, slowly cooling region that early models predicted. Instead, sophisticated computer simulations, and helioseismology, the study of sound waves traveling through the Sun, have revealed a complex three-dimensional structure with temperature variations that ripple through the stellar interior like thermal weather patterns. These temperature fluctuations occur on timescales ranging from minutes to centuries. Sound waves generated by turbulent convection at the base of the convection zone travel downward into the radiative zone, carrying with them slight variations in temperature and pressure. These acoustic oscillations create standing wave patterns throughout the Sun's interior, causing the entire star to ring like a bell with periods ranging from minutes to hours. By measuring these solar oscillations from Earth-based observatories, astronomers have essentially performed a cosmic ultrasound of the Sun's interior. Just as doctors use sound waves to image the inside of the human body, helioseismologists use stellar acoustics to map temperature variations throughout regions that will never be directly observable. These measurements reveal that the Sun's interior is far more dynamic than anyone imagined. The temperature structure changes as sound waves propagate through different regions of the stellar interior. In some areas, the waves encounter slightly cooler plasma and slow down. In others, they pass through regions that are marginally hotter and accelerate. By analyzing thousands of these acoustic modes simultaneously, scientists have created three-dimensional maps of temperature variations throughout the Sun's radiative zone. These thermal maps reveal something extraordinary about stellar evolution. The Sun's interior retains a memory of its formation and early evolution, encoded in subtle temperature gradients that persist for billions of years. Regions that were slightly hotter or cooler during the Sun's youth continue to exhibit these temperature differences today, creating a fossilized record of stellar birth written in the language of thermal physics. The implications extend far beyond academic curiosity. These ancient temperature variations influence how energy flows through the Sun's interior, affecting the rate at which fusion-generated power reaches the surface. During periods when internal temperature patterns align in certain ways, the Sun's energy output can vary by tiny but measurable amounts over timescales of decades or centuries. Climate scientists studying long-term variations in Earth's temperature have begun to recognize correlations between these deep solar temperature cycles and subtle changes in our planet's climate system. While the variations are small compared to human-induced climate change, they represent natural fluctuations that have been influencing Earth's environment throughout geological history. The magnetic field generated in the Sun's interior also responds to these temperature variations in complex ways. As plasma moves through regions of different temperature, it creates electrical currents that amplify and twist magnetic field lines. These deep magnetic processes eventually manifest at the Sun's surface as sunspots, solar flares, and the intricate coronal structures we observe during eclipses. Recent observations from space-based magnetographs have revealed that the Sun's magnetic field exhibits memory effects that span multiple solar cycles. Magnetic structures created during periods of unusual internal temperature patterns can persist for decades, influencing solar activity long after the original thermal disturbances have dissipated. This magnetic memory connects the Sun's deep interior temperature variations to space weather events that affect Earth's technological infrastructure. Solar storms that disrupt satellite communications and power grids may have their ultimate origins in temperature fluctuations that occurred deep within the radiative zone years or decades earlier. The study of these deep temperature variations has also revealed something unexpected about stellar aging. As the Sun consumes hydrogen in its core and gradually converts it to helium, the changing composition creates subtle alterations in how heat flows through the interior. These compositional changes modify the temperature structure in ways that influence the Sun's magnetic dynamo and surface activity. Over the Sun's 4.5 billion year lifetime, these gradual changes in internal temperature distribution have created long-term trends in solar magnetic activity. Some researchers suggest that the Sun may be entering a period of reduced magnetic activity due to evolutionary changes in its internal temperature structure, potentially leading to a cooler, quieter phase that could last for centuries. The precision required to detect these subtle temperature variations represents one of the triumphs of modern observational astronomy. Ground-based solar observatories can measure changes in the Sun's surface temperature of just a few degrees by analyzing the Doppler shifts of spectral lines as sound waves cause the photosphere to oscillate up and down. These measurements require extraordinary stability and precision. The temperature variations being detected are smaller than the difference between a warm day and a cool day on Earth, yet they're being measured on a star 93 million miles away. The techniques developed for helioseismology have become so sophisticated that they can track temperature changes in the Sun's interior with better precision than we can measure temperature variations in Earth's oceans. Space-based helioseismology experiments have pushed these capabilities even further. The Solar and Heliospheric Observatory and the Solar Dynamics Observatory can measure solar oscillations continuously for years without interruption from weather or the day-night cycle. These long-term observations have revealed temperature cycles in the Sun's interior that weren't visible in shorter datasets. The most remarkable discovery is that some of these internal temperature cycles appear to be synchronized with the Sun's magnetic activity cycles in ways that suggest deep connections between thermal and magnetic processes throughout the stellar interior. Temperature variations that begin deep in the radiative zone somehow influence magnetic field generation in the convection zone, which then affects coronal heating and solar wind properties. This thermal magnetic coupling creates a complex feedback system that regulates the Sun's activity over timescales much longer than the familiar 11-year sunspot cycle. Some patterns appear to repeat over centuries or millennia, suggesting that the Sun's internal temperature structure exhibits long-term oscillations that may influence Earth's climate over historical timescales. Archaeological and historical records of past climate variations show patterns that may correlate with these long-term solar temperature cycles. The medieval warm period and the Little Ice Age, significant climate anomalies in human history, occurred during periods when solar magnetic activity was unusually high or low, possibly reflecting underlying changes in the Sun's internal temperature distribution. These connections between stellar interior temperature and terrestrial climate highlight how intimately connected Earth's environment is to processes occurring deep within our nearest star. The nuclear fires burning at 15 million degrees don't just provide the energy that powers photosynthesis and drives weather patterns. They also participate in complex thermal cycles that may influence climate variability over the entire span of human civilization. Modern climate models are beginning to incorporate these solar variability effects, recognizing that understanding Earth's future climate requires detailed knowledge of how the Sun's internal temperature structure will evolve over coming decades and centuries. While human activities currently dominate global climate change, natural solar variations continue to provide a subtle but persistent influence on Earth's thermal environment. The study of solar interior temperature variations has also provided insights into how other stars might behave. Many Sun-like stars exhibit activity cycles similar to our Sun's 11-year pattern, suggesting that the thermal magnetic processes we observe in our nearest star are common throughout the galaxy. Some stars show much more dramatic activity cycles, with periods of intense magnetic activity followed by decades or centuries of relative quiet. These extreme variations may reflect differences in internal temperature structure that depend on stellar mass, age, and composition. By understanding how temperature patterns influence solar activity, astronomers can better interpret the behavior of distant stars and assess the habitability of their planetary systems. Exoplanet researchers are particularly interested in how stellar temperature cycles might affect planetary atmospheres over long timescales. A planet orbiting a star with highly variable internal temperature patterns might experience climate variations that could either enhance or inhibit the development of complex life. The techniques developed for measuring solar interior temperatures are now being applied to other stars through asteroseismology, the study of stellar oscillations. Just as helioseismology reveals temperature variations inside the Sun, asteroseismology can map the internal structure of distant stars by analyzing their acoustic oscillations. These stellar temperature measurements are revealing that Sun-like stars exhibit a wide range of internal thermal behaviors. Some stars appear to have very stable temperature structures that change little over time, while others show evidence of dramatic thermal reorganizations that occur over timescales of millions of years. The diversity of stellar temperature patterns provides crucial data for understanding stellar evolution and the long-term stability of planetary systems. Stars with highly variable internal temperatures might subject their planets to climate changes that occur too rapidly for biological adaptation, while stars with extremely stable thermal structures might provide more consistent conditions for the development of complex ecosystems. As observational techniques continue to improve, astronomers expect to detect even subtler temperature variations in stellar interiors. Future space missions equipped with ultra-precise photometers may be able to measure temperature oscillations in the Sun and other stars with accuracies that approach the theoretical limits imposed by quantum mechanics and thermal noise. These measurements will provide unprecedented insights into the fundamental physics of stellar interiors, including how nuclear fusion rates respond to small temperature changes, how convective motions transport energy through different thermal environments, and how magnetic fields are generated and sustained by temperature-driven fluid motions. The long-term goal is to develop predictive models of stellar temperature evolution that can forecast how the Sun's internal thermal structure will change over millions or billions of years. Such models would allow scientists to predict not just when the Sun will exhaust its hydrogen fuel, but how its temperature patterns will evolve throughout its main sequence lifetime and beyond. These predictions have profound implications for understanding the long-term habitability of Earth and other planets in our solar system. By knowing how the Sun's internal temperature will change over geological timescales, climate scientists can model how Earth's environment will respond to the slowly evolving solar energy input. The story of solar interior temperatures thus connects some of the smallest measurable variations in stellar physics to some of the largest questions about the future of life in the universe. Temperature fluctuations of just a few degrees in regions we cannot directly observe may ultimately determine whether Earth remains habitable for billions of years, or whether our planet's biosphere faces natural limits imposed by stellar evolution. As we drift toward the conclusion of our thermal journey through the Sun, these deep interior temperature mysteries remind us that even our nearest star continues to surprise us with its complexity. The 15 million degree nuclear furnace at the core represents just one aspect of a thermal system so intricate that we're still discovering new layers of structure and behavior. The Sun's temperature story reveals itself as more than a simple tale of hot and cold. It's a narrative about how energy, matter, and time interact in ways that create and sustain the conditions necessary for life to emerge and flourish. From the quantum tunneling that enables fusion at 15 million degrees to the acoustic oscillations that reveal temperature variations throughout the stellar interior, every aspect of solar thermal physics contributes to the delicate balance that makes our existence possible. Tonight, as you rest in the gentle warmth that began its journey in nuclear fire, remember that you're connected to thermal processes that span scales from the subatomic to the cosmic. The heat that maintains your body temperature, the infrared radiation warming your surroundings, the very atoms that compose your being, all trace their origins to temperature extremes that challenge human comprehension, yet operate with the precision necessary to sustain life throughout our solar system. The Sun's thermal mysteries continue to unfold as our understanding deepens and our instruments become more sensitive. Each new discovery reveals additional layers of complexity in the temperature patterns that govern our nearest star, reminding us that the cosmos contains wonders that will continue to surprise and inspire us for generations to come. In contemplating how hot the Sun truly is, we discover that we've been exploring more than stellar physics. We've been investigating the thermal foundation upon which all terrestrial existence rests. The temperature-driven processes that connect nuclear fusion to planetary habitability, and the delicate thermal balance that has made our cosmic journey of understanding possible in the first place. As we approach the culmination of our journey through solar temperature extremes, we encounter perhaps the most mind-bending revelation of all. The Parker Solar Probe, humanity's most audacious attempt to touch the Sun itself, has recently shattered all previous records by diving to within just 3.8 million miles of the solar surface, traveling at an astonishing 430,000 miles per hour through the corona's million-degree plasma. This remarkable spacecraft, protected by a revolutionary carbon foam heat shield designed to withstand temperatures of 2,600 degrees Fahrenheit, has begun transmitting data that challenges everything we thought we knew about coronal heating. As it hurtles through plasma, heated to over 1 million degrees, the probe's instruments are measuring up to 146 different parameters every second, creating an unprecedented real-time portrait of the Sun's outer atmosphere. The initial findings are nothing short of extraordinary. The corona isn't just hot, it's violently dynamic in ways that previous Earth-based observations could never reveal. The probe has detected sudden temperature spikes where plasma reaches over 10 million degrees in localized regions smaller than Earth itself. These thermal explosions, lasting only minutes, release energy equivalent to millions of nuclear weapons, yet occur so frequently that they may represent the primary mechanism heating the entire corona. But here's what makes these discoveries truly revolutionary. The temperature variations the probe is measuring don't follow any pattern that existing theories predicted. Instead of smooth gradients or predictable heating zones, the corona exhibits a chaotic thermal landscape where million-degree plasma exists alongside regions that are relatively cool, creating temperature contrasts more extreme than the difference between boiling water and liquid nitrogen. These measurements are revealing that magnetic field lines act like invisible highways for thermal energy, channeling heat in ways that create the corona's bizarre temperature structure. When magnetic field lines become twisted and stressed by the sun's rotation and convective motions, they can suddenly snap and reconnect, releasing bursts of energy that instantly heat surrounding plasma to temperatures exceeding 5 million degrees. The probe has captured direct evidence of these magnetic reconnection events as they happen, measuring temperature jumps that occur in milliseconds across distances of just a few hundred kilometers. It's like watching lightning strikes made of pure thermal energy, each one capable of heating plasma to temperatures that would vaporize any known material instantly. Even more fascinating is how these extreme temperatures propagate through the corona. Rather than spreading uniformly like heat from a fire, thermal energy in the corona travels along magnetic field lines at speeds approaching the speed of light. This creates a three-dimensional network of thermal highways where million-degree plasma can exist just kilometers away from regions that are relatively cool. The Parker Solar Probe's temperature measurements are also revealing something unexpected about how the solar wind is born. As million-degree coronal plasma expands into space, it doesn't simply cool down as it travels away from the sun. Instead, the probe has detected regions where the solar wind actually becomes hotter as it accelerates, reaching temperatures that exceed those found closer to the sun's surface. This thermal acceleration process appears to be driven by waves of magnetic energy that continue heating the solar wind long after it leaves the corona. These waves, called Alfvén waves, can carry thermal energy millions of miles into space, creating a hot, tenuous atmosphere that extends far beyond anything astronomers previously imagined. The implications of these discoveries extend far beyond solar physics. The hot plasma measured by the Parker Solar Probe eventually flows past Earth as the solar wind, carrying with it thermal signatures that directly influence our planet's magnetic field and upper atmosphere. During periods when the probe detects particularly hot coronal plasma, Earth experiences enhanced aurora activity and increased heating of the upper atmosphere. These temperature variations in the solar wind also affect every other planet in our solar system. Mars, with its thin atmosphere and weak magnetic field, is particularly vulnerable to changes in solar wind temperature. When hot coronal plasma reaches Mars, it can strip away atmospheric particles and contribute to the planet's ongoing atmospheric loss. The gas giant planets, despite their enormous size and distance from the Sun, also respond to solar wind temperature variations. Jupiter's powerful magnetic field captures hot solar wind particles, creating radiation belts with temperatures that can exceed 1,000,000 degrees. Saturn's magnificent aurora displays are directly driven by the interaction between hot solar wind plasma and the planet's magnetic field. Even the outer reaches of our solar system feel the influence of these coronal temperature extremes. The Voyager spacecraft, now traveling through interstellar space, continue to detect the thermal signature of hot coronal plasma that left the Sun decades ago. These measurements provide a historical record of how solar coronal temperatures have varied over the past several decades. The Parker Solar Probe's revolutionary temperature measurements are also transforming our understanding of stellar evolution and the ultimate fate of our Sun. As the Sun ages and its core composition gradually changes, the internal temperature patterns that drive coronal heating will slowly evolve as well. Computer models incorporating the probe's temperature data suggest that the Sun's corona may become significantly hotter over the next billion years as the core temperature gradually increases. This enhanced coronal heating could lead to stronger solar winds and more intense space weather, potentially affecting the long-term habitability of Earth and other planets. The probe has also detected temperature patterns that may be signatures of the Sun's deep interior structure. Certain coronal heating events appear to be synchronized with acoustic oscillations that originate in the Sun's core, suggesting that temperature variations deep within the star can influence the million-degree plasma in the corona. These connections between the nuclear furnace at 15 million degrees and the coronal plasma at 1 million degrees reveal the Sun as an integrated thermal system where energy flows and temperature patterns are connected across the entire stellar structure. Changes in core fusion rates can eventually manifest as altered coronal temperatures, while magnetic heating in the corona can influence energy transport throughout the solar interior. The technological achievement represented by these temperature measurements cannot be overstated. The Parker Solar Probe is essentially a thermometer capable of surviving in an environment where temperatures would instantly vaporize any conventional material. Its heat shield, while reaching temperatures hot enough to melt steel, successfully protects instruments that must remain at room temperature to function properly. This thermal engineering marvel has enabled humanity to directly sample the Sun's atmosphere for the first time, providing ground truth measurements that will calibrate decades of theoretical models and remote observations. The temperature data being transmitted by the probe represents some of the most extreme environmental measurements ever attempted by human technology. Future missions building on the Parker Solar Probe's success may venture even closer to the Sun, potentially measuring temperatures in the chromosphere and transition region where the most dramatic thermal gradients occur. Such measurements would complete our understanding of how energy flows from the nuclear core through all the temperature regimes we've explored on our journey. The European Solar Orbiter mission, working in conjunction with the Parker Solar Probe, is providing complementary temperature measurements from different vantage points around the Sun. By observing the same coronal heating events from multiple perspectives, scientists are creating three-dimensional maps of how million-degree plasma moves and evolves throughout the solar atmosphere. These coordinated observations are revealing that coronal temperature patterns are far more complex and dynamic than anyone anticipated. Rather than stable, well-defined layers, the Sun's atmosphere exhibits turbulent thermal structures that constantly form, evolve, and dissipate over timescales ranging from seconds to hours. The temperature story emerging from these cutting-edge observations paints a picture of our Sun as a fundamentally dynamic, ever-changing thermal environment. The 15 million degree core may burn steadily for billions of years, but the million-degree corona above responds to magnetic and thermal processes that create constant variation and complexity. This dynamic thermal behavior has profound implications for understanding how other stars heat their atmospheres and drive stellar winds. The mechanisms revealed by Parker Solar Probe temperature measurements likely operate in stellar coronas throughout the galaxy, suggesting that hot, dynamic atmospheres may be common features of Sun-like stars. For exoplanet researchers, these insights into coronal heating provide crucial data for assessing the habitability of planets around other stars. A star with particularly intense coronal heating might subject nearby planets to harsh radiation and hot stellar winds that could strip away atmospheric particles and sterilize potential biospheres. Conversely, stars with cooler, more stable coronas might provide gentler space weather environments that could be more conducive to the long-term stability of planetary atmospheres and the development of complex life. The temperature measurements from our own sun's corona serve as a baseline for understanding this crucial aspect of stellar habitability. The Parker Solar Probe's temperature discoveries also connect to some of the deepest questions in plasma physics about how magnetic energy converts to thermal energy in low-density environments. The corona represents a natural laboratory where magnetic reconnection, wave heating, and turbulent dissipation operate under conditions that cannot be replicated in terrestrial experiments. Understanding these heating mechanisms has applications far beyond solar physics. The same processes that create million-degree coronal plasma may operate in the magnetic confinement systems being developed for fusion energy on Earth. The temperature measurements from the corona could inform the design of fusion reactors that must heat and contain plasma to temperatures even hotter than the sun's atmosphere. The probe's discoveries are also revealing connections between solar temperature extremes and fundamental physics. In regions where coronal plasma reaches its highest temperatures, the boundary between classical physics and quantum effects becomes increasingly important. Particle collisions at these thermal extremes can create conditions where quantum mechanical processes influence the behavior of stellar plasma. These quantum effects in hot coronal plasma may play a role in particle acceleration processes that create high-energy radiation and cosmic rays. The sun's corona serves as a natural particle accelerator, where thermal energy gets converted into kinetic energy, launching particles at speeds approaching a significant fraction of light speed. The temperature measurements reveal that these acceleration processes are intimately connected to the magnetic heating mechanisms that create the million-degree corona in the first place. Hot coronal plasma provides the thermal energy reservoir that powers particle acceleration, while the same magnetic reconnection events that heat the plasma also create the electric fields that accelerate particles to extreme velocities. As we synthesize all these revolutionary temperature discoveries, we begin to appreciate that our journey through solar thermal extremes has taken us to the frontier of modern physics. From the quantum tunneling that enables 15 million degree fusion in the core to the magnetic reconnection that creates million-degree coronal plasma, every temperature regime reveals fundamental processes that govern how energy and matter interact under extreme conditions. The Parker Solar Probe's measurements represent more than just numbers on a cosmic thermometer. They provide direct observational evidence of physical processes that operate throughout the universe, from stellar atmospheres to galaxy clusters where million-degree plasma spans distances of millions of light years. These temperature extremes also remind us of our intimate connection to stellar processes that seem impossibly remote from everyday experience. The hot coronal plasma being measured by the Parker Solar Probe will eventually cool and expand to become part of the solar wind that flows past Earth. Some of these particles, heated to over 1 million degrees in the corona, will interact with our planet's magnetic field and contribute to the aurora displays that illuminate our polar skies. The thermal energy that began as nuclear fusion at 15 million degrees traveled through the radiative zone over tens of thousands of years, emerged from the photosphere at 6,000 degrees, and was reheated to over 1,000,000 degrees in the corona. Ultimately reaches Earth as the gentle warmth that makes all life possible. This extraordinary thermal journey connects the most extreme temperature conditions in our solar system to the moderate climate that sustains our biosphere. As you contemplate these final revelations about solar temperature extremes, remember that you're witnessing science at its most adventurous and inspiring. The Parker Solar Probe's journey into million-degree plasma represents humanity's boldest attempt to directly explore one of the most extreme environments in our cosmic neighborhood. Every temperature measurement transmitted by this remarkable spacecraft adds another piece to the puzzle of how our sun works, how stellar atmospheres heat themselves to impossible temperatures, and how the thermal processes that began in nuclear fire ultimately create the conditions necessary for planets, chemistry, and life to flourish throughout the cosmos. The sun's temperature story, from the nuclear furnace of the core to the million-degree corona extending into space, reveals itself as one of the most magnificent examples of how the universe organizes energy and matter into structures of breathtaking complexity and beauty. These thermal extremes, so far beyond anything in human experience, operate with the precision and stability necessary to sustain a star system where conscious beings can arise to contemplate the very fires that made their existence possible. Tonight, as you drift into peaceful rest, you carry with you the knowledge that humanity has successfully touched the sun itself, measuring temperatures that challenge the imagination while revealing the intimate connections between stellar fire and the gentle warmth that surrounds you now. The thermal extremes that power our nearest star continue their ancient dance, converting matter to energy with the same nuclear precision that has illuminated our solar system for over 4 billion years and will continue to do so for billions more years to come. The temperature measurements streaming back from the Parker Solar Probe are revealing something that will fundamentally change how we think about stellar atmospheres and the very nature of heat itself. As this brave little spacecraft continues its death-defying dance through million-degree plasma, it's discovering that the corona isn't just hot in the way we imagined. It's hot in ways that seem to violate everything we thought we understood about how energy behaves in space. Picture this extraordinary revelation. The probe has detected regions where plasma heated to 5 million degrees exists in direct contact with material that's relatively cool, creating thermal boundaries sharper than anything we've ever observed. It's as if someone took a blowtorch and held it next to an ice cube, except both the fire and ice somehow maintain their temperatures without affecting each other. These impossible thermal gradients exist throughout the corona, creating a three-dimensional maze of hot and cool regions that defies conventional physics. But here's where the story becomes truly mind-bending. The probe has discovered that these extreme temperature variations aren't random or chaotic. Instead, they follow patterns that seem to be controlled by invisible magnetic structures threading through the corona like a vast, complex spider web. Each magnetic field line acts like a thermal pipeline, channeling million-degree plasma along specific routes while isolating it from cooler regions just meters away. These magnetic thermal highways create a coronal architecture that's far more sophisticated than anyone imagined. The corona isn't simply hot plasma sitting above the sun's surface. It's an intricate network of thermal channels where energy flows in patterns that would make the most complex computer circuit look simple by comparison. Each magnetic field line carries its own thermal signature, creating a vast information system written in the language of temperature itself. The implications of these discoveries extend far beyond our solar system. The Parker Solar Probe's temperature measurements are revealing that stellar atmospheres throughout the galaxy likely exhibit similar thermal complexity. Every sun-like star may possess its own unique network of magnetic thermal channels, each one creating temperature patterns that influence the space weather environment around any planets that might orbit there. For worlds that might harbor life around other stars, these thermal networks could determine whether planetary atmospheres remain stable over the billions of years necessary for complex life to evolve. A star with particularly intense magnetic heating might create such harsh thermal conditions that nearby planets lose their atmospheres entirely. Conversely, stars with more gentle thermal networks might provide the stable, moderate space weather environments that allow biospheres to flourish. The probe's measurements are also revealing something extraordinary about the relationship between temperature and time in the corona. Rather than heating up gradually like a pot of water on a stove, coronal plasma can jump from relatively cool temperatures to over 10 million degrees in just seconds. These thermal explosions happen so quickly that they challenge our understanding of how energy can be transferred and absorbed in low-density environments. Each of these rapid heating events releases energy equivalent to millions of nuclear weapons, yet they occur hundreds of times every hour throughout the corona. The cumulative effect of these countless thermal explosions is to maintain the corona's average temperature at over 1 million degrees, creating one of the most energetic environments anywhere in our solar system. What makes these discoveries truly revolutionary is how they're changing our understanding of the connection between the sun's interior and its atmosphere. The probe has detected temperature variations in the corona that appear to be synchronized with acoustic waves originating deep within the sun's core. This suggests that the nuclear furnace burning at 15 million degrees somehow communicates with the million-degree corona through a complex network of sound waves and magnetic fields. These connections create a thermal communication system that spans the entire star, allowing changes in the core's fusion rate to influence coronal heating patterns, while magnetic activity in the corona can affect energy transport throughout the solar interior. The sun reveals itself as an integrated thermal organism where every temperature regime influences every other through subtle but persistent feedback mechanisms. The Parker Solar Probe's journey through these extreme temperatures is also providing unprecedented insights into how matter behaves when heated to such incredible extremes. In regions where coronal plasma exceeds 5 million degrees, the distinction between individual particles begins to break down. Electrons move so fast that they approach relativistic speeds, while atomic nuclei collide with energies that can create exotic forms of matter not found anywhere else in our solar system. These ultra-high temperature regions serve as natural laboratories for studying physics under conditions that cannot be replicated in terrestrial experiments. The probe's instruments are measuring how matter transitions between different states as temperature increases, providing data that will inform our understanding of stellar physics, cosmology, and the fundamental behavior of matter and energy under extreme conditions. So what have we discovered on this extraordinary journey? through the most extreme temperatures in our solar system. From the relatively cool sunspots dancing across the photosphere at 3,000 degrees to the impossible 15 million degree nuclear furnace burning at the sun's heart. We've explored thermal extremes that challenge everything we thought we knew about heat itself. We've witnessed how the sun defies logic, growing hotter as we move away from its surface, creating million-degree coronas that shouldn't exist according to our everyday understanding of physics. We've seen magnetic fields act as invisible thermal highways, channeling energy in ways that create temperature gradients more extreme than anything found on Earth. The Parker Solar Probe's revolutionary measurements have shown us that our nearest star isn't just hot, it's magnificently, impossibly, precisely hot in exactly the ways needed to sustain the delicate cosmic dance that makes life possible throughout our solar system. Tonight, as you drift into peaceful rest surrounded by the gentle warmth that began its journey in nuclear fire 15 million degrees hot, remember that you carry within you atoms forged in stellar furnaces, just like our sun. You are not separate from these cosmic temperature extremes, you are part of them, a temporary arrangement of stellar matter that has achieved the remarkable ability to contemplate the very fires that created you. Sweet dreams, fellow travelers in this magnificent, scorching, life-giving cosmos.